Have you ever wondered what light really is? Is it just a simple phenomenon that we take for granted every day, or is there more to it than meets the eye? It's a question that has fascinated scientists and philosophers for centuries. From the ancient Greeks to the modern-day physicists, the nature of light has been a subject of intense debate and curiosity. Is it a wave, like ripples on a pond? This idea suggests that light spreads out and travels through space in a manner similar to how waves move through water. Or is it a stream of tiny particles, like bullets from a gun? This particle theory proposes that light is made up of small, discrete packets of energy that travel in straight lines. In the early 19th century, a simple experiment provided a groundbreaking answer. This experiment was not only elegant in its simplicity but also profound in its implications. This experiment, conducted by English scientist Thomas Young, would forever change our understanding of light and its behavior. Young was a polymath, with interests ranging from medicine to Egyptology, but it was his work in physics that left an indelible mark. It became a cornerstone of modern physics. The results of Young's experiment were so compelling that they influenced the development of quantum mechanics and the study of wave-particle duality. Young's double-slit experiment, as it came to be known, offered compelling evidence that light, in fact, behaves like a wave. By shining light through two closely spaced slits, Young observed an interference pattern that could only be explained if light were a wave. This discovery had profound implications not just for our understanding of light but for physics as a whole. It challenged the prevailing Newtonian view of light as particles and opened up new avenues of scientific inquiry. So, how did this seemingly simple experiment revolutionize our view of something as fundamental as light? The answer lies in the details of the experiment and the groundbreaking conclusions that were drawn from it. Let's delve into the experiment itself and uncover its secrets. By understanding the setup, the observations, and the interpretations, we can appreciate why Young's double-slit experiment remains one of the most important experiments in the history of science. Before we can grasp the significance of Young's experiment, we need to rewind a bit. Before Young, Isaac Newton's corpuscular theory of light held sway. Newton proposed that light was made of tiny particles. While this explained some aspects of light, like reflection, it couldn't account for others, such as diffraction. Diffraction is the bending of light as it passes through narrow openings or around obstacles. This is where Young's experiment comes in. It provided a definitive way to test whether light was truly made of particles, or if it behaved as a wave. With a simple setup and an elegant design, Young was poised to challenge centuries of accepted wisdom about the nature of light. Imagine a beam of light. Now picture that beam passing through two tiny, closely spaced slits. What would you expect to see projected onto a screen behind the slits? If light were made of particles, you'd expect to see two bright bands on the screen, each band corresponding to the light passing through one of the slits. However, that's not what Young observed. Instead, he saw something much more intriguing, a pattern of alternating bright and dark bands. This unexpected result provided crucial evidence in favor of light's wave-like nature. Let's delve deeper into the details of this groundbreaking experiment and understand how this unique pattern, known as an interference pattern, occurs. To understand the interference pattern, we need to think about light as a wave. Imagine the ripples spreading out when you drop a pebble into a pond. Like those ripples, light waves have crests, high points, and troughs, low points. When two waves meet, they interact with each other. This interaction, known as interference, is at the heart of Young's experiment and the key to understanding the peculiar pattern it produces. Section 5. The interference pattern, where light and dark intertwine. Now let's go back to the two slits. When a light wave passes through each slit, it acts like a new wave source. These waves then spread out and overlap. Where the crests of two waves meet, they reinforce each other, creating a bright band on the screen. This is called constructive interference. Conversely, when a crest meets a trough, they cancel each other out, resulting in a dark band. This is called destructive interference. This interplay of constructive and destructive interference creates the alternating bright and dark bands, the hallmark of the interference pattern. This pattern is a dead giveaway that what we're seeing is the result of wave behavior, not particles. Section 6. The aftermath. A revolution in understanding light. Young's experiment had a seismic impact on the scientific community. It provided the most compelling evidence yet that light could behave like a wave. This challenged Newton's corpuscular theory, which had been the dominant model for over a century. While initially met with skepticism, Young's findings eventually gained acceptance, paving the way for a new era in our understanding of light. The implications of this discovery went far beyond just revising our picture of light. It laid the groundwork for the development of wave mechanics, a fundamental theory in modern physics that describes the behavior of matter as waves. Section 7. Young's experiment in the modern world, from lasers to holograms. The impact of Young's double-slit experiment extends far beyond the annals of history. This groundbreaking experiment, first conducted in the early 19th century, fundamentally changed our understanding of light and wave interference. It provided the first clear evidence that light behaves as a wave, a concept that was revolutionary at the time. It continues to shape our understanding of the universe and underpins numerous technologies we rely on today. The principles derived from Young's experiment are not just confined to theoretical physics. They have practical applications that touch our daily lives in myriad ways. From lasers, which exploit the principle of wave interference to produce highly focused beams of light, to fiber optics that enable high-speed internet by transmitting data as light pulses, the applications are vast and varied. To holography, which uses interference patterns to record and recreate three-dimensional images, the technology that allows us to create stunning visual displays and even potential future applications in data storage and medical imaging. The legacy of Young's experiment is evident in countless aspects of modern life. Whether it's the smartphone in your pocket, the computer on your desk, or the advanced medical equipment in hospitals, the principles of wave interference are at work. Even the study of the cosmos, my own field of expertise, relies heavily on the principles first demonstrated by Young. The ability to analyze light from distant stars and galaxies has opened up new frontiers in our understanding of the universe. Telescopes, for instance, use the wave nature of light to peer deep into the universe, allowing us to observe phenomena that are billions of light years away. This has led to discoveries about the formation of galaxies, the behavior of black holes, and the expansion of the universe itself. Revealing distant galaxies and unlocking the secrets of the cosmos, Young's experiment laid the groundwork for modern astrophysics and continues to inspire new generations of scientists and researchers. Section 8. Beyond the visible, exploring the universe with waves. The beauty of Young's experiment lies in its simplicity and its profound implications. It not only revealed the wave nature of visible light but also paved the way for understanding that other forms of electromagnetic radiation, like X-rays and radio waves, also behave as waves. This realization has revolutionized our ability to study the universe. Radio telescopes, for example, use the interference patterns of radio waves from space to create images of distant objects, revealing phenomena hidden from optical telescopes. In essence, Young's experiment opened up a whole new window into the cosmos, allowing us to explore the universe in ways that were unimaginable before. Section 9. The Enduring Legacy, a Cornerstone of Modern Physics. More than 2 centuries after it was first conducted, Young's double-slit experiment remains a cornerstone of modern physics. This simple yet profound experiment, first carried out by Thomas Young in 1801, demonstrated the wave-like nature of light, challenging the then prevailing particle theory of light. By shining light through 2 closely spaced slits and observing the resulting pattern on a screen, Young provided compelling evidence of interference, a hallmark of wave behavior. It serves as a powerful reminder that even seemingly simple experiments can lead to profound discoveries that reshape our understanding of the universe. The double-slit experiment has since been adapted and expanded upon, revealing even more about the dual nature of light and matter. It has become a fundamental demonstration in physics education, illustrating key principles of wave-particle duality and quantum mechanics. The experiment's enduring legacy lies not just in its historical significance but also in its continued relevance to cutting-edge research in fields like quantum mechanics and optics. Modern variations of the experiment have been conducted with electrons, atoms, and even large molecules, each time confirming the wave-particle duality and deepening our understanding of quantum behavior. Researchers today use sophisticated equipment like lasers and quantum computers to explore these phenomena further. It serves as a testament to the power of human curiosity and the elegance of the scientific method in unraveling the mysteries of the natural world. The double-slit experiment exemplifies how a simple setup can yield insights that challenge our most fundamental assumptions. It underscores the importance of questioning established theories and being open to new ideas, a core principle of scientific inquiry. As we continue to explore the cosmos and delve deeper into the quantum realm, the lessons learned from Young's experiment continue to guide us. The principles uncovered by this experiment are not confined to the laboratory. They have practical applications in technologies like quantum computing, cryptography, and even in understanding the behavior of materials at the nanoscale. The experiment's influence extends far beyond its original scope, impacting various scientific and technological fields, reminding us that the universe is full of wonders waiting to be uncovered, if only we dare to look. The double-slit experiment is a beacon of scientific exploration, encouraging us to push the boundaries of what we know and to seek out the unknown. It is a powerful symbol of the endless quest for knowledge that drives humanity forward, inspiring future generations of scientists to continue the journey